And the plan for today is to go through the material related to calculations, and then on Wednesday we'll take up the rather limited topic here of accounting. I know the title of this is Medical Calculations and Accounting, but it's not an accounting class. There are just certain basic principles that a medical assistant will need to know about working in the office, because depending on the practice, you'll have the potential for being basically a clinical medical assistant or an administrative medical assistant. And if it's a small practice, you may be doing both.
Okay.
Now, no one expects you to be an accountant, which is good.
I hope so.
Yeah. And in reality, accounting is a specialized field. But there are certain basic things that you need to be able to do that are in the realm, generally speaking, in the realm of accounting, such as, reconciling bank statements, balancing checkbooks, that sort of thing, and understanding the differences between income and expenses, or known as credits and debits in accounting terms. So that's what you'll do. The work that will be here in the assignment next week is where you're going to use EHR Go to actually look at the electronic health records of a couple of patients.
Okay.
And say how you would, sitting in an office, discuss their concerns about their bills.
Ooh, non-payment.
Well, objection to charges. It's
Okay.
not necessarily non-payment, because
But
we do have to deal with that. The accounts receivable have a timeline. Accounts receivable are what people owe you and haven't
yeah.
paid. And so there's a timeline associated with that. Usually when we send out our bills, we expect to be paid within typically 30 days. Because that's what our vendors expect. So we need to have that cash flow coming in so we can pay our bills.
Right.
So never expect that. There are times when your patients will say to you, I can't afford that. And then you get to work out payment schedules and so forth. And how that's handled from an accounting standpoint is up to the practice's actual accountant. A practice needs, there's a difference between an accountant and a bookkeeper. A bookkeeper does many of the things that an accountant does, but is not trained in doing the kind of financial analysis that accountants are trained in to look at the financial health of an organization. The bookkeeper makes certain that everything is entered properly and keeps the practice fully apprised of its financial condition, but doesn't do a lot of the analytical things. And generally speaking, a business will have an accountant, usually someone who is designated by taking exams and getting permission, getting licenses, a certified public accountant who is not an owner of the business to keep the books and do the reporting. But the people in the office have to know how to record things. like income, like expenses. That makes it a lot easier for the accountant to do their job. Um, and the reason you want to make it easier for the accountant to do their job is they usually charge by the hour.
Okay.
So, you know, being responsible to your employer is making certain that the accountant is not doing background work that should have been provided to them so that they can do their job of preparing the company accounts. And of course, the bigger the practice, the more complex that is. And it's why large practices and hospitals have huge accounting departments. So anyway, we'll get into some of those issues on Wednesday. But today I really want to looking at calculating flow rates for parenteral administration, for IV administration of drugs. And then we'll talk about we'll spend a little bit of time looking at dispensing quantities and what we call days supply, meaning how long will this prescription actually last? How many days? And we've spent a lot of time looking at already at drug calculation errors and the consequences thereof, but it's an ongoing issue because errors are can be a significant problem, not just to the patient, but then can cause a lot of trouble within an organization. I know of practices that won't tolerate any error. They will fire anyone who makes an error. And those errors can be drug calculation errors, or they can be really foolish things that people do, like using a syringe and not instantly putting it into a sharps container. And I know that Tel has taught you that that's your first consideration, is it goes from the patient to the sharps container immediately. You don't set it down on the counter. That's an accident waiting to happen.
Yes.
So we'll get started on looking at these things. I want to first go to, let's back up here.
And the sharps thing is a huge error. My son got vaccinated at his last appointment, and one of the MAs laid the needle down uncapped next to his leg. And I wasn't mean, but I kind of freaked out because no child likes to get vaccinated. And so they're kind of kicking and crying and in pain already. And I was like, I'm sorry, but you need to put that in the sharps container immediately after use. I was like, you can't lay that next to any patient.
And it needs to be within reach of where you are using the sharp object. And that's one of the things that some practices are not good at. And, you know, so yeah, good. We have to be willing to call people. I can remember one time when my mother-in-law was still with us, she was on Coumadin because she had an implanted pacemaker, and she had a bleed. And we had her in the ER down in Wheat Ridge, and in walks this nurse, happened to be a male nurse, but that's not relevant. In walks the nurse, gloves up, washes his hands, gloves up, and then an emergency occurred, and they needed to have everyone immediately helping with this emergency. And my mother-in-law wasn't considered an emergency, so he apologized and left, and was gone for, I don't know, 10 minutes maybe. And when he came back in, I watched him very, very closely, and I think he saw that. But I wanted to be sure that when he came back in, that he switched out gloves, washed his hands, etc. And he did. And I made sure that I thanked him for that. But, you know, too often people get in a hurry, they're not thinking, and they make those mistakes. And it's good to call them on it because once
People.
the accident occurs, it's too late.
Hmm.
If an accident occurs, I mean, the problem is we get complacent. It hasn't ever happened before. Yeah.
It can always happen, though. That's the
Mhm.
mentality you have to have.
Yep. And the other thing you have to remember is that accidents, by definition, are preventable. So, by someone anyway. I remember one time talking to a cop years ago, and he said um, he was talking to, I guess he was talking to kids at our school, and he said um, 35% of automobile accidents, there is absolutely no indication that anyone involved in the accident did anything to avoid it.
Wow.
Yeah. And
That's
sometimes
shocking.
it's hard. My wife got broadsided at a traffic light one time. She was making a left turn on an arrow, a green arrow. It had just turned green. She looked up, and she's a very careful driver. She looked up. There was nothing in sight. She starts to make the turn, and a Chevy Tahoe hits her at 45 miles an hour running the light.
Oh my goodness.
You know, there was no way that she could have avoided it.
No,
Now, the witnesses said that the guy was looking down at his phone
of
as he
course.
went through the intersection. So he could have avoided it.
Yes, he could have. You
But
are correct.
my wife didn't stand a chance because he was out of sight, and then it was down a hill, so he came up over a hill and hit her.
Oh my goodness.
So, you know, it's a case of when these things happen. But that's another example of why accidents are almost always preventable one way or another. One of the you know, so you remove as many of the sources of trouble as you can, and that's why we train people about Sharps procedures. If that's not there, then that's one accident that's not going to happen. So anyway, let's look at what's going on this week, and I'll quickly go through um, the discussion. Um, the first discussion of the week is about accounting. And this, this really is um, um, understanding what those roles are going to be. So you're going to do a little bit of research on this, and it's worth doing because it will be expected that you have some idea. I don't know if you still have the big black medical assisting book.
Yes, I do.
There is a chapter
Oh,
in there, or a
okay.
couple of chapters in there on the administrative duties of a medical assistant. And one of them, as I recall, does include a discussion of at least one includes a discussion of accounting type duties that an assistant may have. It's worth reading, and that can be a reference.
Okay, perfect.
Okay, so there's that. You may want to, we'll talk a bit about discussions in a moment, but I'm going to back up here and we're going to go to the second discussion of the week, which is really where we're going to put a lot of our time today. This is about flow rates for parenteral administration. This is really not a great picture for the topic. It does give you one idea of one method of injection. You've been through Pharmacy 107, so you know what the three injections that we use, intramuscular, subcutaneous, and intradermal, that we teach you
Yes.
at the school. IV medication, we don't do a lot of teaching for that. So that's something that if you're expected to do it as a medical assistant, you need to insist on being properly trained.
Okay.
Because if you don't set an IV correctly, it can cause enormous discomfort to the patient when you start pumping stuff into their tissues instead of into their veins.
Oh, oh, yes.
Yeah, I've had a number of students tell me that that's happened to them, and they say it's very
It's it's
uncomfortable.
very painful.
So
Oh,
when we calculate a dose for injections, it's not too bad. But when we are looking at um, infusion for IV administration, there's two ways that we inject IV. We can either stick a needle into a vein and just push out in one motion, empty the contents of the syringe into the vein. That's called a bolus injection. And it's fairly common, and in fact, but more often when we are setting an IV, it's going to be for some sort of infusion, a continuous administration over time, and it has to be at a specific rate that matches the instructions from the physician or the prescriber. And so we will look at those at those kinds of calculations during today's lecture, and we're going to concentrate on that. We'll spend some time on days supply, but that's a fairly straightforward calculation, which I think when you see, you'll say, "Oh yeah, of course, that's easy." But I really want to get into those. But let's go ahead and get started. We have, we'll have, on Wednesday, we'll have the in-class activity. That should be, yeah, okay. That I'll have to fix. That's in the wrong spot. Um, So we're going to look at the week's assignment. And here, the assignment for the week is all about the calculations, days supply and parenteral. So you can download the worksheet by clicking here in the prompt. And what I'm going to do is screen share it. Let's find it. Oh, come on, you're not cooperating with me.
that's Mondays. That's what the day I was having so far. My Zoom wanted to update and all of that, so I was like, oh, lovely. I wish you would have done this last night.
Yeah, yeah, they will do that. And it's kind of annoying.
Yes, sometimes technology feels like it has a mind of its own.
Yeah. Aha. Here we go. Okay, so you should be able to see this assignment sheet here.
Yes.
Okay, so it starts off with flow rate formulas. And flow rate is really about how much material goes into the patient in a specific time, like an hour or a minute. And there are times when we'll use both. Most of the time, all of the time, if we're using an electronic pump, also known as an electronic controller. We'll be calculating the flow rate in terms of milliliters per hour. Okay, that's how they're set. The pumps themselves are, you need to have only, a very short period of training on those pumps. I'm sorry that we didn't have anything like that at the school to give you some idea of these. You may or may not do anything like this as a medical assistant in an office. I have seen it done um, in medical offices, but I've also seen offices that very clearly were not set up for it.
Okay.
So it'll depend on your practice, but the whole idea is to look at the flow rate, which they call FR here, is the volume to be administered and the amount of time, the total volume to be administered and the amount of time you're supposed to take to do it. The physician will tell you infuse over 4 hours, or they might even give you a flow rate, but they will tell you to infuse something over a space of time.
Okay.
It might be, it can be anywhere up to, they've got 24 hours written here, but in general, they generally don't go much over 12 hours. And in a practice setting, it's going to be a much shorter time, a few hours at most. Largely because your patient isn't going to want to lie there on some bed in the practice and twiddle their fingers for 6 hours while something goes in. And in general, when I've seen it, it's usually no more than a couple of hours of time.
Okay.
But an infusion pump, the electronic controller, is calibrated in milliliters per hour. And generally speaking, the maximum rate at which they can function is basically a liter an hour. They go up to 999 milliliters per hour. That's fast, and there are times when it will be needed.
Okay.
But usually those are emergencies. Although if you have to rehydrate a patient, and I've seen this done, it might be over the course of an hour or two, you would put in that much material. The problem with such high rates is they can be painful to the patient, because what you're doing is pumping a foreign substance into the blood. Whether that, and even if it's normal saline, that's not what our blood is composed of. I mean, that is the concentration of sodium chloride in plasma for sure, 0.9%. But it's in its pure form, that's not what our plasma has. Plasma has an enormous number of other components. So what happens when you put something that is not normal into a vein? The lumen responds with pain and inflammation, and it can get pretty uncomfortable. So we try not to make these things fast, whether they're a bolus or an infusion, because the potential for discomfort to the patient. Now, life-saving makes us discount that discomfort. And most people are perfectly willing to have a little bit of discomfort if it's going to keep them alive. So what we do is if we get an order such as this, 1 liter of normal saline infused over 24 hours, well, our volume is a liter. We have to convert that to milliliters.
Okay.
Okay. So remember, the rate is always with an infusion pump is always milliliters per hour.
Okay.
The physician here has specified 24 hours. So we simply divide 1,000 milliliters by 24 hours, we get 41.67 milliliters per hour. We cannot set the controller to fractions of milliliters, so we round it off.
Okay.
So um, some of the more advanced pumps that we have are capable of being calibrated to 1/10 of a milliliter, but most places will not have them because they're significantly more expensive than the 1 milliliter version, or the whole number version. So you probably won't see those. So it's easy enough to see how to do these calculations. And when I get done going through this, I'm going to pull up something I prepared that I will actually post after the end of the class
Okay.
into the shell. Um, so you'll have some practice problems here.
Great.
Another way of doing a an administration is not to use a pump, but to let gravity do the work for us. We call this manual or gravity feed. If you look at later on when you pull this up, if you look at this video, there's a person in there who will take you through this, and she makes it very clear that there is a difference that when we're doing drip calculating how to set these things up. She's very clear about that. Um, the but when we are doing that, we don't have something we can set at milliliters per hour. In fact, we have to calculate the flow rate in terms of minutes. So that's why this particular part, okay, of the formula uses a small t. This is time in minutes. So we calculate first the volume, divide it by the number of minutes over which we're going to be infusing it, and then we multiply it by what we call the drop factor. The drop factor is the number of drops that the apparatus you're using that will equal 1 milliliter.
Okay.
There are 4 different um, types of apparatus that use this. I mean, they all look the same, but they're all rated differently because the size of the dropper in the IV line, there is a drip chamber. And you watch the drug will come out of the bag, go through a dropper, drop into the chamber, and then be infused into the patient. There is a void space there of air that never goes into the patient. So you don't need to worry about that. There's a big worry that people have about injecting air into patients' veins. You have to inject a pretty significant amount to have any possibility of endangering the patient. So we don't worry about that. These things are designed to work to where there's always, the drip chamber is always about half full, and then that's going into the patient.
Okay.
We hang, when we are using an infusion pump, it doesn't matter where we put the bag because the pump is pulling stuff out of the bag, whether it's lying on the floor or hanging on a pole. And
Right.
we always hang it on a pole, but that will pull it out. When we're using this gravity feed, we are dependent on making certain that that bag is sufficiently above the patient so that there will be a constant pressure in that chamber to move things into the vein. And that bag setting for a gravity feed or manual feed is 36 inches above the heart. So if the patient is sitting in a chair, then we would not have it 36 inches above the vein. Usually the same place you're going, or on the arm, uh, or in the case of the little bitty needles they use for things like, the happy juice they give you at the dentist when they're going to pull teeth. Um, the it will usually be in a large vein, either in the hand or the arm. If you're sitting in a chair, that's going to be below the heart. So you have to have the bag at least 36 inches above the patient's heart. A patient lying in a hospital bed, pretty much the arm and the heart are on the same level. But we have to make sure of that. So, and part of that is to make certain that that there is that the actual gravity is pulling this stuff, pushing things down into the arm at higher pressure than the blood pressure, because what you don't want is actually the heart putting stuff into the bag, putting blood into the bag by backflow into the needle. That's one of the reasons we have it above the heart instead of below. If we put it below the heart, the blood would be flowing into the bag instead of the contents of the bag flowing into the patient. So we want to be sure of that. So here we have this drop factor, which is the number of drops per milliliter, and there are four. There are two basic categories. One we call a macro apparatus. These are bigger drops. These include 10 drops per milliliter, 15, and 20. Most hospitals, most of the places that I've seen, because these sterile, what we call venoclysis sets, are expensive. Most places are not going to have all three of those 10, 15, or 20 drop per milliliter sets. Mostly they'll go with something in the middle. Occasionally you're going to need a set that is 10 drops per milliliter for a high volume infusion. So that 15 or 10 or 20 is called the drop factor. It's the number of drops per milliliter. The micro set is 60 drops per milliliter, and that's usually used for when your infusion rate is about 1 milliliter per minute or less. And it's all about error. If you are using just say you have one milliliter a minute and you want to use a 10 drop factor, 10 drop factor set, that would be 10 drops a minute. Well, if you're off by one drop, you're off by 10%. So we use the 60 for those because that's 60 drops per minute, 1 per second. If you're off by a drop or two, we're only off by a much less than that 10% error. So we will use the microset for low rate infusions, meaning a milliliter a minute approximately or less. And we'll use the macro sets for higher amounts. Okay. So how we do that is we calculate that flow rate. In this particular case, we've got normal saline at 150 milliliters per hour. Now note, we're just given a rate. We're not given a volume. We don't have to calculate the rate, except that this is per hour. So we have to divide that into minutes. We have to separate, so we have to change 1 hour to 60 minutes. And then when we divide 150 by 60, we get 2.5 milliliters per minute. Okay. Now, if we're using a 15 drop factor 15 set, we multiply then that rate by the drop factor. So we go from milliliters per minute and we multiply that by drops per milliliter. Milliliters cancel out and we get drops per minute. So we can see that here. they put this into one quick calculation. I generally prefer people to do things stepwise when they're learning these things. But we divide 150 by 60, we get 2.5, multiply 2.5 times 15, and we get 2.25 milliliters per minute, or 2.5 milliliters per minute times 15 drops per milliliter, we get 37.5 drops per minute. Well, we can't count half a drop.
Right.
What's missing here is that this has to be rounded off
The nearest whole number.
to the
Okay.
nearest whole number. So this would be 38. So
Yep.
we have an error here. You know, at 38, we're giving a little bit more than is being requested, but it is by 1/2 out of 37.5. In other words, a very, very small percentage error. So
Okay.
we're worried about that. But this is also why I urge students to not round anything off until they get to the very end of the calculation. Because then if you round off at each stage, you are introducing a little bit of error at each stage, and it becomes cumulative.
Yes.
And there are some of those errors that if you just move them through, they would have canceled each other out. But for the most part, they will give you a cumulative error. So we wait until the end. And with the advent of calculators, that's pretty easy. And you will use calculators. Nobody expects you to do all of these calculations in your head. Thank goodness.
Yes.
But it's easy enough to see. In this case, you're going to have a problem here that has 20 drops per milliliter as the drop factor. So as I say, my preference is to calculate the rate in milliliters per minute and then multiply by the drop factor,
Okay.
rather than get too caught up in setting up complicated equations. These aren't particularly complicated, but they get a little messy after a while.
I tend to do my equations step by step because it just helps me understand it better. So looking at that one, I was kind of confused, but you broke it down, so it makes sense.
Yeah, I always prefer to break these things down. So here we are. So there we see one little one little thing to remind you is fractional drops are not possible.
Okay.
So they always get rounded off.
Okay.
So let's go on down. There's some other calculations here that are that can be done. But let's take a look, and there's this, you come out with the same answer no matter what you do. But you can calculate this based on the dose. Okay, so in this particular case, we're using heparin, which is an injectable anticoagulant. And heparin is a biologically derived product. So its potency has for well over a century been measured in what we call units of activity. A unit of activity is it's a measure of potency, and it disappears from the calculation the same way that milligrams or micrograms will disappear, and all we're doing is giving a volume. So the actual questions here, whether we're working in units or grams or even down here in milliequivalents, which are used for things like electrolytes. And it has to do with chemical combining power. How that's calculated isn't particularly relevant to this class. But again, a milliequivalent can be converted directly into grams of material if you know the chemistry. But units cannot. And part of the reason that they cannot is that they depend on a biological assay measurement and a biological process, which essentially by definition um, is not consistent enough to where we can put a weight on these things. Now, things are changing in the pharmaceutical industry, but we will be using these for a long time. We also measure the activity of things like penicillin in units of activity. So and other antibiotics are measured in units. You've also seen it in vitamins, vitamin D, vitamin E, vitamin A. These are in general um, reported in units of activity. And you cannot compare a unit of heparin with a unit of vitamin A, for instance, because
Okay.
they're entirely different assays and entirely different concepts for how they're measured. So be aware that you'll see this. Don't ever worry about it because, as I say, we don't inject units, we inject volumes.
Okay.
Okay. So if we're looking at the dose, if we are looking at, in this particular case, 1,000 units of heparin in 24 hours, we can, and unless you are given a drop factor for your apparatus, assume it's a pump.
Okay.
So you're going to be doing milliliters per hour. That's that is the answer we're going to want to come up to. Okay. So in this particular case, we're going to be giving 41.67 units per hour if we divide 1,000 by 24, 1,000 units by 24.
Okay.
Don't
That
round
can't,
this off.
don't round these off?
Don't round it off.
Okay.
Okay. Okay, so we know that we've got 1,000 units in 500 milliliters of normal saline. We were told that. So this is not a calculation. So what we want to do is calculate a volume of material that's going to be given to the patient in an hour using this dose. So
Okay.
we have, this is actually rearranged. If we had 41.67 divided by X milliliters, X equals 500 over 500 or 1,000 units over 500 milliliters, and we rearrange that, then we come up with this equation.
Okay.
Okay. So that comes out to 20.84 milliliters. And again, we cannot inject that. We cannot set a pump at that level. So this becomes 21 milliliters per hour. Now you'll note that it's supposed to be over 24 hours. And at 21 milliliters per hour, it will actually go in a little bit faster.
Okay.
The nice thing about these infusion pumps is that they have alarms on them. When the material in the bag runs out, the pump detects that that air has moved into the line, and it shuts off and sends an alarm to the nurses.
Okay.
But you'll note that it's not a whole lot faster. Okay.
No, it's not.
Yeah. So what we have here is, again, another one is looking at a milliequivalent of potassium chloride per hour over 8 hours. So that's goes back up here. What we have got is here they tell us we want 1,000 units over 24 hours, and we have to calculate how many units per hour. Here they tell us 1 milliequivalent per hour. and we have a bag that has 10 milliequivalents in 1,000 milliliters of normal saline. So what's the flow rate? So we know we can skip this first set. We know that we have 1 milliequivalent per hour.
Okay.
So 1 milliequivalent over X equals 10 milliequivalents over 1,000 milliliters. Rearranged, we get this equation. Milliequivalents cancel out. We only have milliliters, and we get 100 milliliters per hour. So that's another way of looking at these dosing. From my standpoint, which method you use depends on the information that you're given in the problem.
Okay.
In this particular case, we're told that we're going to put 1,000 units and 500 milliliters and give it over 24 hours. Well, we know that we're going to be injecting 500 milliliters over 24 hours. So we can actually calculate using either method. Okay. But again, use the method that it is clear you can do. So let's do a quick stop at days supply. The days supply means how long will the medication last in days. Every prescription is not open-ended. In other words, you're not given a bottle of 1,000,000 pills and say, you know, take them as long as you need them. You are given specific amounts. Yeah, don't we sometimes wish? Now, of course, you know, we're talking about prescription medications. OTC medications, you go down and you buy 1,000, you know, you go down to Costco and you buy, you know, 2,000 ibuprofen tablets.
Right.
And take them as needed. A practice, I think, ought to be discouraged. Going back to the fact that there is no such thing as a safe drug, even an OTC drug. But nonetheless, if we look at this and we look at this formula, AD is the amount dispensed by the pharmacy. A is the amount per dose, and F is the frequency. X is just a time sign. That tells you how many days. So if we take a look at this quick example, a patient has been given amoxicillin, 875 milligrams twice a day. The pharmacy dispensed 14 tablets. Okay. When the prescription is written by the doctor, it may include this. This is not a hashtag. It's a number sign. It includes this symbol and followed by a number. That number can be in Arabic or Roman numerals, and will tell the pharmacy how many units of drug are to be dispensed. So it's a pretty easy prescription to fill, although the pharmacist will almost always just check to make sure that this number matches the rest of the prescription. This would read, as a prescription, it would read amoxil or amoxicillin, 875 milligrams, PO/BID, and then followed by this number sign and 14.
Okay.
Now that tells us we've got 14 tablets go out. That's the amount dispensed. The amount per dose is 875 milligrams, and we have given 875 milligram tablets. So 875 milligrams, there's 1 tablet per dose. Also, yet when the prescription label comes out, it doesn't say this gobbledygook on it. What it says is take 1 tablet twice a day for 7 days. So what we will see is 14 is the total amount. We have 1 tablet per dose, 2 doses per day. Dose cancels out, tablets per day, tablets cancel out. We end up with 7 days. So this prescription will last 7 days. Now that's pretty easy to see, but it gets interesting when you have other kinds of drugs that we won't be getting into today. But some drugs are not given with the same dose all the time. Coumadin or warfarin is often given with 1 dose 3 days a week and a different dose 4 days a week. So figuring out the day's supply is a little more complicated, but it can certainly be done. Okay, quantity to dispense is sort of the reverse. Okay, the amount per dose times the frequency times the number of days. This number of days has been referred to up here as the day's supply.
Okay.
Most prescriptions will either specify a number of tablets. Well, all prescriptions should specify a number of tablets and a number of days. There are a few exceptions. Nitroglycerin, which is to be taken as needed for angina, chest pain,
Yes.
is generally handed out in bottles of 100, and the patient is told, take it when your chest hurts, when you feel the pain. So there's no way of predicting how long such a prescription will last. But for the most part, we see this. Now here, we've got another Amoxil, 500 milligrams BID for 7 days. What we have is on hand, we have 250 milligram tablets. Okay. So we calculate tablets per dose using the formula we discussed last week and used dose prescribed or dose prescribed divided by dose on hand times the vehicle. In this case, the dose prescribed is 500, dose on hand is 250, and it's tablets. So what we have is we're going to have 2 tablets per dose. That's the amount per dose. It can be tablets, capsules, milliliters. This applies to liquid drugs as well. And so the frequency is twice a day and the number of days is 7. So we've got 2 tablets per dose times 2 doses per day times 7 days. Dose cancels out, days cancel out, and we get 28.
Okay.
Okay. So that's, basically the reverse of days supply. So those are the questions that you have here. I would also point out that this last one on problem 15, oxycodone 5 milligram PO should precede Q4H. Our route of administration always precedes the frequency.
Yep.
Okay. So that should be, now, does that mean that every doctor will always do that? Well, not necessarily, but for the most part, that's their training. And they will do that correctly. Okay, so it's now 10 a.m. Let's take a short break.
Okay.
And then we'll come back and go through something I prepared for further discussion on these topics.
Okay, perfect.
So I'm going to pause the recording. Don't let me forget to resume it when I get back.
Okay, I will let you know.
Okay. And we'll move on to something that I prepared to try and address this as well. And as I said, I'll be uploading this later on. So in this particular case, I started with days supply. That's fairly simple. So basically, it's exactly what we've looked at here. The days supply is the amount dispensed divided by the product of amount per dose and frequency. And the abbreviated form is listed here. So we go down here to this prescription, amoxicillin, 250 milligrams. This II is Roman numeral 2 caps, PO, TID, and then number 60. So that tells us that we're going to be taking 2 capsules 3 times a day by mouth. So this number 60 is what he's telling us. So when we take, the actual instructions to the patient, don't mention 60, even though that will appear on the prescription label.
Okay.
But it's, the instructions are clear: take 2 capsules by mouth 3 times a day until gone. The until gone may or may not be there, but in general, we want patients to take the entire prescription of any antibiotic. So we have, so we just plug that in. We've got the amount dispensed is 60, and then we have 2 capsules per dose, 3 doses a day. We multiply all that and divide it. We get 2 times 3 is 6, 6 into 60, 10 days. And that is the day's supply. So again, it's a pretty straightforward calculation, but occasionally you'll have a patient that'll say, well, how long am I supposed to take this? So that's one of the reasons that we may want to do this calculation of days supply.
Okay.
And we can do this with solids and liquids. So if we are going to take, say, 2 teaspoonfuls by mouth 3 times a day, then we're going to have a volume that the patient will receive. So they should then receive 60 teaspoonfuls, which is 20 tablespoons, which is 10 ounces. So it depends on the material. So usually speaking, all you have to do is look at the prescription. You can figure this out.
Okay.
Let's go back to this flow rate. And again, volume is the volume being dispensed is the rate times the time, V equals RT. We can arrange this and solve for any of these. Hi, Jen. We can rearrange this and solve for R by simply dividing both sides by T. We can solve for T by dividing both sides by R. And so we can determine any of these variables, but we obviously have to know 2 of them in order to do that calculation. So if we're looking at delivering 1 liter of normal saline over a period of 4 hours, if we're going by electronic pump, it's going to be 1,000 milliliters equals the rate times 4 hours. And then it's just a simple solution to divide both sides by 4 hours. We get 250 milliliters per hour. So that's a fairly straightforward. It's it doesn't get any more complicated. The numbers will be different, but it doesn't get any more complicated than that.
Yeah, they're actually.
Now, if we are looking at manual delivery, we need to know 2 things. First off, we need to know the same information, the time that is going to, the amount to be delivered and the amount of time in order to calculate the rate. And we have then, in order, if it's a manual delivery, we have to know which type of venoclysis set we're going to use. Okay. As we said, they all have these drop factors, 10, 15, or 20, and then 60. So we have a second calculation to do, which is the drip rate calculation, the rate times the drop factor. In this case, we calculate 1,000 milliliters in 4 hours, we want to know how many milliliters per minute. We do that calculation by dividing 240 into both sides, and we get 4.17 milliliters per minute. Okay, again, we don't round that off. So we then multiply that by the drop factor. We're assuming in this particular case that we're going to use a 15 drop venoclysis set. So we simply multiply the milliliters per minute times 15 drops per milliliter. Milliliters cancel out. We get 62.5 drops per minute. Again, this is where we round it off to 63. Had we rounded off this to 4, after calculating this and assume that it's 4 milliliters a minute, then we would calculate 60 drops per minute. So that's why we don't round off until the very, very end. Okay, makes sense?
Yes, it makes perfect sense.
Okay. So the next part of this is a little more complex, in that if we're actually delivering a drug, we have some other calculations to do first. And this is a little bit of additional material. It's not going to appear in in an exam or an assessment, but it is something to be aware of that we can calculate. In this particular case, a pretty simple calculation. We are told that we're going to be delivering 200 milligrams of some drug in 500 milliliters of saline over 4 hours via pump. This is the only thing that counts. When looking at this, it doesn't matter how much drug is in the bag. We're delivering a volume. So this is merely a volume rate problem. So we would be dividing 500 milliliters by 4 hours and calculating that at 125 milliliters per hour going into the patient. Okay, makes sense?
Yes.
Okay, so when you're looking at these problems, you need to say to yourself, what am I seeing? Okay, now the next problem is slightly different. Let's look at it a little bit here. We're going to have 500 milligrams of a drug in 1 liter of 5% dextrose and water. Here we want to deliver 500 milligrams per kilo over 8 hours via the pump. Okay. So we have a couple of things. We're dosing by weight. Okay, so there's a couple of principles here. First off, we're dealing with dosing at 5 milligrams a kilo, and we have a patient who weighs 176 pounds. So we have to first convert pounds to kilograms, right? Okay. So, and so we divide by 2.2 pounds per kilogram. So if we divide that, we're going to get, that's going to equal 6 pounds divided by 2.2 pounds per kilogram. And that's going to, and that will equal, I'm just going to give you the answer here, that will equal 80 kilograms. That's the weight of the patient. So that's our first thing. So what we have to do is calculate the amount of drug that is to be delivered to the patient in 8 hours. So now we multiply 5 milligrams per kilo by the kilo weight of the patient. So the second thing we do, second we find the total dose. And we do this by multiplying the prescribed dose, 5 milligrams per kilogram, by the 80 kilogram weight of the patient, because 5 milligrams is the amount that goes into a 1 kilogram patient. Obviously, that's not going to be an adult, right? Obviously, someone who's 176 pounds is adult size. So we multiply that by 80, and we're going, and this is then is going to equal 400 milligrams. Okay, so 80 times 5 is 400. So this 400 milligrams is less than the total amount of material in the bag. Okay, because there's 500 milligrams in this liter. So now we know what a total dose is. And in this case, so we use the D times Q, as they use here, divided by the H, the dose on hand. So the dose prescribed times the vehicle, which in this case is going to be a volume, over the amount of drug that is in that volume. So that's going to be 400 milligrams times 1,000 milliliters, which is what 1 liter is, right? And we're dividing that by 500 milligrams. If we go back to last week's assignment, when we calculated all those doses, remember all that? That making sense?
So they said, oh, well, we've got a really good children's hospital right here. Let's take it there.
Are you with me?
Yes,
Okay.
I'm sorry. I was on mute still.
Okay, no problem. Okay, so now we simply do the math. And again, what this amounts to is we're going to actually deliver 800 milliliters. Okay?
Okay.
So if we do that calculation, we're going to be delivering 800 milliliters. So, but this again is over 8, let's do this, 8 hours according to the problem. So now we simply plug that into the rate formula and we get 800 milliliters divided by 8 hours. And that's going to equal 100 milliliters
Per hour.
per hour. Okay. So there we have, that's how we figure that out. So the key here is always figuring out what the dose is, the total dose that's going to be given to the patient, and then go back to our formula that we use, dose prescribed, time divided by the dose on hand times the either whatever you want to call it, the quantity, the vehicle. So in this case, we have to be able to identify what these are. We calculated the dose prescribed based on this set of information. We are told that we are being given 500 milligrams of drug, the dose on hand, and in a vehicle of 1 liter. It doesn't matter that this is D5W, that's what the doctor ordered. There are some drugs that are not compatible with saline. And so we have to deliver it in D5W. So we have all the information. We have to go through and pick it out. And then it's just plugging it into the formula. Does this make perfect sense?
It does.
Okay. So let's look at a yet again more complex problem. Okay. And that problem is we're putting 50 milligrams of drug C into 500 milliliters of dextrose 5% in normal saline, D5NS. And we're going to deliver this at 2.5 micrograms per kilo per minute via the pump. The patient weighs 132 pounds. So again, convert pounds to kilos. And we get 132 pounds, divided by 2.2 pounds per kilo, and that's going to equal 60 kilograms. Okay, so we convert that first, and now we have to find the total dose. So we do that again by multiply 2.5, let me use a decimal point, not the British way, micrograms per kilo per minute, okay? So that's going to be times 60 kilos. And that's going to equal now 150 micrograms per minute. Okay. This is an important number. This is where we would stop if we were doing this by gravity, because this is the dose per minute the patient is going to receive. Okay. But we're going to assume a pump. So now we have to convert minutes to hours. Okay, and that's going to be, we're going to multiply 150 micrograms per minute by 60 minutes per hour. And that will equal 2.5 times, or 150 times 60. So we pull out our calculator. And that's going to equal 9,000 micrograms per hour. Okay. So that's what we come up with for this, 9,000 micrograms per hour. Just you following along with all this?
Yes, I am. I was actually calculating it too.
Oh, good. Always check me. So we have 9,000 micrograms per hour going into this patient. Why do we want it per hour? Because we're told first off via pump, okay?
Okay.
So with this, we're looking at 9,000 micrograms per hour. Now 9,000 if we go back to D times Q over H, D, the dose prescribed, is going to equal 9,000 micrograms per hour. Q is going to equal 500 milliliters. We know that because we're told that at the very beginning. Note that I have written this out, okay? And H, the dose on hand is going to be 50 milligrams. But remember, we cannot have micrograms and milligrams in the same problem.
So it would be 500 micrograms.
Actually, it's going to be 50,000.
50,000.
Right. So
That's right. 3
times
zeros.
1,000 micrograms per milligram equals 50,000 milligrams, micrograms rather.
Yep.
Okay.
So it's adding 3 zeros.
Right. Now note that we keep the dose in micrograms per hour. Okay.
Okay.
So what we're going to do now is set this up. So dq over H becomes 9,000 micrograms per hour times 500 milliliters, and we're dividing that by 50,000 micrograms. So micrograms are going to disappear and we're going to have milliliters per hour. Okay. So again, let's use our calculator. We've already calculated the 9,000. So we're going to multiply that by 500 milliliters. And then we're going to divide that by 50,000 micrograms and end up with
90 milliliters per hour.
Yep, 90 ml per hour. Okay, so that's what we're going to have. So it's a little more complicated, only because there are just more steps. But
Right.
the real key to solving these kinds of problems is to dissect the question, okay? We don't, the first thing we have to do is look at the rate of delivery. This is the dose prescribed, 2.5 micrograms per kilo per minute. We know the patient weight because we can read the chart, or maybe we've just weighed the patient ourselves. So we know what the patient weighs. So we know that it's going to be milliliters. We're going to be calculating milliliters per hour because it's via pump.
Okay.
So we have to determine how much this patient is going to receive. Remember, this 2.5 micrograms is a dose for a 1 kilo patient. So we always, if we're dosing by weight, we're always multiplying by the weight of the patient.
Okay.
Okay. If we're dosing at specific rate over time, like per minute, and some very potent drugs, things like isosorbide dinitrate and others, are often administered at these kinds of rates because they are rapidly metabolized. So we need to keep a specific amount in the patient over time. So we are looking at pumping this drug in quickly. at this rate. So we then count. So the first thing we do is we figure out that this patient's going to receive this total of 150 micrograms a minute. We have to convert that to hours. So we figured it was 9,000 per hour. Plug that. So this then becomes D for this problem,
Okay.
right? So the rest of it falls out by using that formula we used last week. Now let's do a couple of things with the venoclysis set. Okay. In this first one, we figured that the rate was going to be 500 ml divided by 4 hours equals 125 ml per hour. Okay, so that was the answer. When we go back and do the same calculation, we've already done the an important part of it right here. But we now, we look at this one and we start with, we're dosing at 125 milliliters per hour.
Okay.
But now we have to divide by 60 minutes per hour to get the amount that's going to go in per minute. So if we do that calculation, we find that this is 2.08 milliliters per minute. Okay. So now we have everything we need to do the rest of this problem. So now we simply multiply, if I can type, by the drop factor that we are given. So here we're using a 15 drop factor set. So we're going to then, this is going to be 2.08 milliliters per minute.
You can't play with that.
Times 15 drops per milliliter. So we go back to our calculator. And again, we haven't rounded anything off. So we're not going to do that until the end. So we multiply this times 15. No, we're supposed to multiply by 15. And we get 31.25 drops per minute. Which we round off to 31, right?
Okay.
Makes sense. Now on number 2 here, I can take out the extra word here. We're going to use a 10 drop set, but we go back up to number 2, and we've already solved this for milliliters per hour. So all we have to do is start with 100 milliliters per hour is going to be divided by, convert, we have to convert to milliliters per minute.
Okay.
So we have 100 milliliters per hour divided by 60 minutes
Per hour.
per hour. And we're going to get 1.67, but we'll go ahead and use the calculator. 1 point, and we're going to leave it there. on our calculator equals 1.67. We'll write this down as a rounded off form.
And so they use our fence pockets on the highway from here to wherever.
So we get this, and now we multiply by the drop factor, right?
Mhm.
So we get 1.67
Milliliters.
milliliters per minute
So the other day.
times 10
10.
drops per milliliter. And we get what?
16.7 drops per minute,
Right.
which would be rounded up to 17, correct?
Yep.
Okay.
17
Drops per minute, I'm sorry.
Yep, 17 drops per minute. So now we've solved that. We could have used any of the macro sets. I threw in this one just to give a variation.
Okay.
But let's take a look at the third problem. So let's do that. We're going to do this problem now with a venoclisis set of 60. Let's see what we come up with. Now we already figured out the milligrams per minute, but we went to 90 milliliters per hour. So what we start there, we're only concerned with the volume. That's why we're going to just start with this 90 and come up with what we have. So so we have so we want to convert to milliliters per minute. So we've got 90 milliliters per hour divided by 60 minutes per hour. And that's going to equal 1.5 milliliters per minute.
Okay.
So now we're going to multiply
By the drop factor. Okay.
We're going to get 1.5 milliliters per minute times 60. We're supposed to use a micro set, 60. So we're going to get, that's going to equal what?
90 drops per minute.
90 per minute. So we see that this is a pretty fast rate.
Yes.
So this might not be the right set, but this is what we were told to use. So so there we're looking at something with this big calculation, but you can do about 90. That's 3 drops every 2 seconds, and these venoclisis sets actually have a dial on them that allow you to set close to what your rate is, but you still time it.
Okay.
Anything above about 90 drops per minute is going to be very close to a continuous stream and very difficult to control. So this was an example of what these numbers do. This is very high.
Okay.
Now, I'm going to point out something here. 90 milliliters per hour and 90 drops per minute. It turns out that when you're using the micro set, that the number of drops per minute is equal to the number of milliliters per hour. That is just a mathematical relationship because we divided this by 60 minutes per hour and then multiplied it by 60 drops per milliliter. So basically,
Okay.
we reversed this calculation. So one method of looking at it is take a look at that rate and see if it's reasonable to use a micro apparatus. That makes
Okay.
sense?
That does make sense.
So I'm going to save that. So I will get this posted. It's now 10 minutes till 11. You have some discussions to catch up on. So what I'd like you to do is spend the rest of this morning's class time working on those discussions.
Okay.
I will make sure that you can still submit the discussions. Let's see, we want to go to, here we go. Want to go back to the assignment. So let's go take a look at, and what I want you to do is catch up on the discussions you've missed. So let's take a look at, these and make sure they're still open. This one is kind of interesting. This is supposed to be a discussion. Let's back up. Back out to the modules. Let's do this again.
I didn't want to stop. You know, the rule was that if I was going to listen to it, I had to pay it. Right.
Okay. So this will work.
So it was funny. So do you like to paint? Well, I'm talking about, I live in an attic.
All right. Okay. So I'm going to give this till the end of this week because I would like you to go ahead and get them done.
Okay.
And taking its time. Come on. Don't lock up on me. Thank you. Let's go ahead and change this one.
Just to add some color and stuff. So I'm doing different kinds of paint like that, like dipping. Similar to that. That's cute. So that top, I mean,
Okay.
so my daughter Elizabeth, this is a rug. A rug. So there's no perspective.
Oh, okay.
And I don't remember what this is. Because I saw it. So,
All right. So, yeah, let's have you start working on these. I will pause the recording at this point. Michaela, if you have any questions after you review this recording, please contact me. But I'd like you to go ahead and get started as well on the assignment and discussions for this week. So so that I will now pause the recording. Okay, Ariel.
Oh my goodness, I'm so sorry. I didn't know I was still on show or not showing myself under my like 6 windows of stuff. I'm sorry.
You were. I was just going to say it's 10 after 12, so it's about time to end class.
Okay.
How far have you gotten with these discussions?
I'm working on the first set still.
Okay.
I I haven't submitted anything yet though.
Well, if you can get caught up today, that would be useful.
Okay, I can try that.
Okay, excellent. Do you have any questions as a result of today's class?
No, I feel pretty good about it. Did you want me to try to complete the assignment as the week 3 assignment between now and Wednesday, or are we going to focus on that next class?
We will focus on that next class.
Okay,
If you want to get started on it, I mean, solving the problems and stuff, go ahead.
okay, okay,
Okay?
great. Well,
We'll
I
take
will
a
see
look
what
at
I
it
can
again
get
next
done
month.
today.
Yeah, because I want to make sure that Michaela understands it as well.
Okay, perfect.
Okay, and we'll spend some time on some very, very basic stuff about the administrative function and accounting in class on Wednesday as well.
Okay,
Okay?
sounds great.
Okay, well, have a good couple of days, and I'll see you Wednesday morning.
Sounds great, Mike. You as well.
Thank you.
Bye.
Bye now.